This is our second column video while I'm away, a short video. When we talk about column design, like anything else in reinforced concrete design, we're using the strength design method. And we've been through this before with beams, both flexurally and relative to shear. And so we know what strength design is all about. You basically have a design capacity of your member which has to be greater than or equal to the factored or the required capacity that's on that member. In Chapter 9, which is just a setup chapter, we are only concerned with axial capacity. That's sort of a fallacy because columns never have just axial load upon them, but for right now, in Chapter 9, that's what we're going to consider. If we think about just axial load capacity of a reinforced concrete column, then, like we've seen before in strength design, we are going to say the design axial capacity, phi Pn, it's got to be greater than or equal to the required axial capacity, P sub u. And so that's basically what we are going to look at. You already know from the required capacity side, you already know about the load combinations. You already know that there's different types of loads, dead load, live load, snow load, wind load, all those other loads. You know that there's load combinations. So you might be given a problem that just says P sub u is equal to 400 kips, or you might be given a problem that says the service dead load is 100 kips, the service live load is 500 kips, the service snow load is 200 kips, and you might actually have to re-enter those load combinations that we talked about way early in the quarter. You might have to go back to them, and you might have to actually calculate a required capacity. Most of our discussion, however, really has to center around the design axial capacity, the phi Pn side of that philosophy. We know that the ACI code will give us a phi value, and that there's probably some formula associated with calculating the nominal axial capacity Pn. And you're right. The phi value is going to really be based on whether we have a tied column or a spiral column. Now, based on those videos that you just saw between the type of failure that occurs potentially when you have a tied column versus a spiral column, which phi value do you think would be lower, the tied or the spiral? If you think about it for a moment, since the tied column failed in a fairly explosive fashion, while the spiral column took a very long time to fail and sort of went through a situation where you saw a lot of spalling, but it didn't fail catastrophically, it would stand to reason that the phi value for a spiral column should be higher than the phi value for a tied column, and that is correct. You're going to see a little bit later in the chapter that the phi value for a tied column is 0.65, whereas the phi value for a spiral column is 0.75. So again, that's reflective of the increased ductility that you saw with a spiral column. But anyway, so the code, the ACI code, is going to give us the phi values, and there's going to be some formula that you have for nominal axial capacity. Again, recognize we're talking in Chapter 9 just about axial capacity, which is, again, not really going to be the case, but we'll talk about it right now. So, anyway, what type of code requirements does the ACI code speak of? Well, you can look in your book at page 264, and they're going to talk for a page and a half about various code requirements. And so that would be probably the place that I would refer to in your book as we talk about these things briefly. The big thing with code requirements is going to be the percentage of steel. Now, the way that we calculate the percentage of steel is based on the gross area of the column. So if I have a column that's 20 inches wide and 12 inches deep, let's say, the gross area of that column is 12 by 20, is 240 square inches. When we say percentage of steel, we're talking about the percentage of steel, of the vertical steel, as opposed to the overall gross area of the column. So if I was to say, hey, my vertical steel is making up 1% of the gross area, then that would be 1% of 240 square inches if my column was 12 by 20. And so that would mean that I'd have an area of vertical steel of 2.4 square inches. The ACI code is going to tell us that that vertical steel really has to fall between 1% and 8% of the gross area. Okay? In reality, your percentage of steel is probably going to be more along the lines of 1, 2, or 3%, somewhere in that neighborhood, rather than 6, 7, or 8%. 6, 7, or 8% doesn't sound like a lot of steel, but when you start really looking at it, it's an enormous amount of steel in a column. So that's probably the primary thing that you'll see over and over again, is they'll talk about the percentage of vertical steel relative to the gross area. Why do you think percentage of steel in a column would be important? Why would they limit it to 8%? Although I've already told you that I doubt you would ever get near 8%. And the reason is they are concerned about, they don't want a situation where you have too much rebar congestion. So this picture shows a column, and it shows beams that frame into the column. Again, everything's monolithically cast in concrete frames, reinforced concrete frames. But I think you could probably look at this picture and start to say, looking at all the steel that I have in the column, looking at all the steel that I have in the beams, looking at all the stirrups, looking at all the ties, it seems like, maybe my concrete in this situation might have a tough time working itself around all of the bars and making sure that I truly act, or it truly acts, in a composite fashion. That's the reason that they're going to limit you to, working between the 1% and the 8% threshold. This probably meets code. I'd say this right here is probably about a 6%, I'm guessing, probably about a 6% of the gross area of the column. So again, it's very, very easy to get congested very, very quick. The other thing to think about, and we saw this in an earlier picture, is that where you splice the column bars, from one pour to another, all of a sudden you might have 10 bars that are being spliced, but as soon as you put the cage down for the next height of column that's going to be built, all of a sudden you're doubling those bars up. So congestion can occur very, very quickly. Again, what other code requirements are you going to see on page 264? Well, one thing, they talk about the minimum number of vertical bars. They'll talk about, the minimum number for a rectangular column being 4 bars. And if you're using some sort of triangular shaped ties, 3 bars. And even if you're using spiral columns to get good connection between the vertical steel and the spiral, they'll talk about the minimum being 6 bars. So they'll talk about those things. The spacing between ties, that's another one. They'll talk about when your ties shouldn't be less than number 3 bars when for the vertical bars. But they'll talk about the center to center spacing of the ties, not more than 16 times the diameter of the longitudinal or the vertical steel, or 48 times the diameter of the tie bars. Or a third thing that they'll talk about as far as spacing is the least lateral dimension of the column. So if I had a 12-inch by 20-inch column, my ties would at least be no more than 12 inches apart. So the spacing between ties is going to be really important. They'll also talk about spirals, and they'll talk about spirals won't have diameters less than 3/8 of an inch, and the clear spacing between them must not be less than an inch nor greater than 3 inches. So, there's a lot of code requirements, and again, I would refer to page 264 and 265 because they sort of outline them. Chapter 9, the capacity formula. This is on page 267, and I would take a look at that. Again, the capacity formula on page 267 is given to you as phi PN. But if you notice very quickly that one formula is given for a spiral column, one formula is given for a tied column. The actual formulas themselves, basically what they're doing is they're giving you the capacity of the concrete portion of the column, and then a capacity for the steel bars, the vertical steel bars. So you'll see like gross area minus the steel area. That's just the area of the concrete. And then they say 0.85 F prime C. They're basically just giving you a maximum, sort of capacity. Cut down, of course, by your phi factors for the spiral and then the ties. That's an all right. Those two formulas are okay. Again, this is chapter 9, so this isn't the whole ball of wax that we're talking about yet. But I mean, those are fine formulas to at least take a look at.